Welcome to a lesson with Dr. Powell. Let's take a look at a proof that the ring of integers is a Noetherian ring, that it's Noetherian. We're assuming it's a ring, but we're going to prove that it is Noetherian for a number field, finite extension of Q. Um, we know by the primitive element theorem that we have a primitive element, and then with that primitive element, we can form a power basis for K as a vector space over Q. In particular, if you take that power basis with starting with L right here, and you take its minimal polynomial, which is monic. I mean, you can divide out by the first guy or just consider the characteristic polynomial of the action of L written as a matrix. In any case, we get this, and we actually can multiply L by something, get alpha, so that alpha will be integral, will be in the ring of integers over Q, or in K over Q. So, and that can be done by taking the least common multiple of the denominators. So thinking of the denominators of these other coefficients, take the least common multiple of the denominators. So anytime you multiply t to any of these guys, you'd have an integer. So if we did that, and we let alpha be equal to TL, notice that you plug TL into here, you're going to get t to the n times L to the n. Here, let's see, you get t to the n times a n minus 1 times L to the n minus 1. Basically, we're going to get this exact same polynomial when we plug this in, except just multiplied by t to the n, which would work. So we would get that this is a root of that. Okay, so in that way, we can have a power basis for the ring of integers that's made up of an integral element. Okay, well, this is a power basis for K as a vector space over Q, but all the elements of that basis are in OK. All right. So let's think about what our goal is. We want to show that the ring of integers is Noetherian, and so we kind of have a setup at least. We found a basis for K as a vector space over Q of integral elements, and the goal is to create with respect to that basis, we're going to create a map that in the end, let's just kind of zoom ahead, takes us to Zn. That's going to be injective, and that's actually going to give it to us, because Zn itself is Noetherian, and OK can be thought of as a submodule of that, and it'll definitely be Noetherian. So we're going to build up with that. The idea that we need is the trace of the extension of K over Q. So we're going to be looking at the endomorphisms of K into the complex numbers. And so this sum is over all of those. So the trace is the trace of an element is simply just the sum of all the conjugates of that element with respect to those endomorphisms, just taking sigma of what you have here as sigma goes through all those endomorphisms of this extension, and you add that up, that's the trace. Okay, so this trace form, if you have like an A times B, so you have like two inputs multiplied together, it's pretty clear that it's symmetric bilinear. We can see how sigma goes into everything and splits, and a constant can come out, and addition and so forth. It behaves just like a bilinear form should, and it's symmetric because multiplication is commutative here. And that being the case, we can represent it as if we have a basis. Suppose we have a basis like VI, labeled as VI. We could have a matrix representing this bilinear form where the two inputs can be written as vectors with respect to that basis, and you write the input right over here as a row vector and here as a column vector, and you can multiply it out, and that'll actually give you the trace of just W times U if these are just considered elements of K. So this is a function which, so the trace is a function right here with domain K, and it's symmetric bilinear, so we can represent this, represent it by a matrix. Now the trace function is a sum of, we're taking a sum of these different conjugates. That actually is one of the coefficients for any minimal polynomial that we have of elements of K over Q. And those polynomials have coefficients in Q. So the output of this trace function is actually in Q itself. Okay. And similarly, if you take something in the ring of integers, well, the monic polynomial just has coefficients that are integers themselves. And so the trace will be an integer. Okay. Now, in particular, if this were a basis even, then the matrix that we have for the trace will consist of integer entries, because the different entries look like this. So they're just, so we're going to have an integer matrix. All right. So this is so we've just created an integer matrix for the trace form with respect to basis right here, this basis, right, power basis right here. Okay. Now something to note. What if we take a matrix like this, where we have our power basis going down, and then we're taking our different conjugate, like in one column, and we're taking conjugates of that column and to get all the other columns. Now, if we were to take this matrix and multiply it by its transpose, that's kind of like taking a dot product of a row and another row. Well, in that case, you know, like this times this, you could factor the sigma out of it if you'd like, the sigma 1 out of it, sigma 2 out of it. And it looks like you're actually just taking a sum of conjugates of the same thing for every entry of the result. And it's true. When you multiply this out, you actually do get the trace matrix that we wanted, that we had before, with respect to this power basis that we had of this integral element. So let's just call that matrix that we get this way M. And we know in particular that, okay, we already talked about this matrix M, that it had integer entries. But not only that, see this, since we decomposed it as A times A transpose, A is a Vandermonde determinant, or a Vandermonde matrix. And that is, and its determinant is a Vandermonde determinant. And so, and we know that that determinant is non-zero if, well, you can express the determinant of that. There's a nice formula for that where where basically you're taking different conjugates, which are just different roots of your minimal polynomial that are and that are distinct, and subtracting them in a product. And you're doing, and that product is going to be non-zero if all those roots are distinct. So if this is a separable extension, which we have with this with the filled extension, so if the number filled extension, so if this is a separable extension, then we automatically have the determinant of each of these parts is non-zero, and hence the determinant of M itself is non-zero. Okay, so we have a matrix M that has integer entries, and its determinant is non-zero. Let's keep looking a little further. So let's let M be a map, and it can just, with respect to, so like a vector space map, or a linear homomorphism, linear transformation of vector spaces. So let's suppose, and but let's restrict it to this ring, which is a subset of that vector space. And we have a map that takes us from for vectors in here, say, that are written with respect to this basis, to vectors in here. That's because the output of the trace form is Well, actually, let's see why this is, in particular, when we see why it's z to the n, um, why that's the case. Notice that if I take m and then I'm going to think of this gamma as being an element of OK, but also written as a vector. So like m times a column vector here. And if you look at the different entries of it, well, the first entry is like putting a row vector that has a 1, 0, 0, 0 on the front. But that's the same as the trace form of just 1 times gamma, which we know is an integer because this is because 1 times gamma is an integral element. Similarly here, if I have a 1 here, that represents the element alpha here, and so we get trace of alpha times gamma, and that's also an integral element because alpha is integral and gamma is integral, and we're working a ring. So we end up getting that actually the output of just gamma is actually in Zn, because all these entries are going to be integers themselves. In a similar way, we could get a trace form with respect to any basis here, and we're going to be getting the trace of different elements in K here as well. So we'd end up getting something in Qn anyhow. But it's important to us to actually have a map that goes from OK to z to the n. And we know that this map is injective because we knew that the matrix M had a non-zero determinant. So Zn itself is Noetherian, and OK is isomorphic to a submodule of a Noetherian ring, which makes it Noetherian in and of itself. And we also know that inside of OK are integral elements, which actually span all of K if you took that span all of K if you took coefficients in Q. So we know that in particular over Z, they're linearly independent. So it has OK must have Z rank, N. It can't have must have Z rank exactly equal to N. It can't have anything more than N in particular. Because it's injective into Zn, and it has but it has a basis, or it has a collection of things that are linearly independent, and there's N of them. And so we actually get that OK has Z rank N, and it is Noetherian. And that concludes that little, at least, description of a proof. Thanks for watching.